Welcome to lesson number 1 of the Softmax section. As of right now, we have effectively coded and discussed the theory behind a basic perceptron model and a more complex deep neural network. However, both of these networks were similar in the sense that they were designed to separate a dataset containing only two labels, 0 or 1. While the perceptron model dealt with linearly separable data, our deep neural network dealt with the separation of a more complex dataset. In this section, we'll take this one step further by discussing multi-class datasets and the theory associated with these datasets. The term multi-class dataset simply refers to datasets that contain more than two data classes. This means that 3 or more labels are present in the dataset, whereas before, we had only dealt with datasets that had two labels, 0 or 1. This introduces brand new obstacles for data classification. The first crucial difference we face between dealing with binary datasets as opposed to dealing with multi-class datasets is the replacement of the sigmoid activation function. As discussed earlier, the sigmoid function is a very useful tool to use for classifying binary datasets. It ranges in probability values between 0 and 1. The predicted probability of a point being 0 as it infinitely approaches the negative region of a model, and reaching close to 1 as it approaches positive infinity. And as you saw, takes the form of the following equation, which converts the variable x, the score of a point, to a probability. This is nothing new, we've already covered this in the last 3 sections. These properties of the sigmoid activation function make it an ideal candidate to be used for classifying binary datasets. However, it is not feasible to use this model for multi-class dataset classification. Its span limitation between 0 and 1 makes this difficult. So here we introduce a new activation function that is capable of dealing with multi-class data. That is the Softmax function. The Softmax function is a useful activation function for scenarios involving multi-class functions. And before we fully jump into the workings of the Softmax function, let's take a look at an example of a multi-class dataset to better understand how these datasets are processed through our neural network. Imagine you are designing a neural network that is capable of distinguishing between different types of sports balls. The network should be able to distinguish between a soccer ball, a basketball, and a volleyball. As there are 3 distinct classes to identify, it can be seen that this is a multi-class data set. Now, in the process of identifying these objects, the network must first take some inputs from the object that is to be identified. This can include things such as weight, texture, color, and size. After these inputs are fed into the neural network, they are manipulated by the weights and bias values of the connections between the input layer and the output layer. Notice how there are 3 output layers, since we're dealing with 3 mutually exclusive classifications. We'll look more into the outputs momentarily, but just think of how previously we only dealt with a single output layer, which simply returned the probability of a point being in the positive region or not, 0 or 1. However, with multi-class classification, suppose we passed in the inputs x1, x2, x3, and x4, which relate to weight, texture, color, and size of some random ball, and we fed it into our neural network through some feed-forward operation. This manipulation eventually returns some score value for each of the ball types. Since there are 3 outputs, we end up with 3 scores. So let's assume after passing our inputs throughout the entire depth of the neural network, as the inputs are constantly being combined through the weights and biases of our network, eventually the network outputs 3 scores, such that the chances of our ball being a soccer ball gets a score of 2, the basketball gets a score of 1, and finally the volleyball gets a score of 0. These scores are nice to have, I guess, but I don't know about you, they don't really mean anything to me. Unless I'm able to convert these scores into probabilities, in order to make these values practical to use for a prediction. The first important thing to consider during this conversion is that the relative magnitudes of the scores must be maintained. This means that a score of 2 must have a higher probability than a score of 1, and similarly so when comparing a score of 1 to a score of 0. That being said, it's clear that by looking at these scores, the inputs of the random ball that we passed into our neural network most likely corresponds to that of a soccer ball. Alright, so the first big condition is that the relative magnitudes must be maintained. The second thing is to remember that all probability values must add up to 1. Both of these requirements can be satisfied using the softmax activation function. That's exactly why, for multi-class classification, we must use the softmax function as it satisfies the two conditions. The softmax function has the following equation. This equation refers to the probability of some score m when there are n number of classes present in the data sets. So what you would do is for each score m, e to the m is divided by the summation of the exponential of all scores, namely e to the m divided by e to the 1 plus e to the 2 plus e to the 0. This equation ensures that the relative magnitude of the scores is maintained, and also ensures that all output probabilities sum to 1 as required. To get a better visual at this, in our particular case, if we sub the numbers into the softmax function, to obtain the probability of our ball being a soccer ball, sub in the score e to the 2, and divided by the exponential summation of all other scores, e to the 2 divided by e to the 2 plus e to the 1 plus e to the 0, which results in a value of 0.67. We do the same thing for the probability of the point being a basketball. E to the 1 divided by e to the 2 plus e to the 1 plus e to the 0, which returns a 0.24 probability of the ball being a basketball, and finally doing the same thing for the volleyball results in a probability of 0.09. Therefore, the inputs, the attributes of the ball we passed into our neural network, result in scores of 2, 1, and 0 after being multiplied and combined through various bias and weight values of our network. And then, that's where we apply the softmax function. We apply it to our final layer, which then determines probabilities of a 67% chance of the ball being a soccer ball, 24% chance of the ball being a basketball, and a 9% chance of it being a volleyball. Therefore, our ball is more likely to be a soccer ball than anything else. Alright, we have now found an appropriate activation function that deals well with the classification of multi-class data. The feed-forward process to determine the probability of something being what it is very similar to how we did it for binary classification. We're passing our input nodes through activation functions in every node of every hidden layer, except now this time, in the output layer, we have to make use of the softmax function to convert our final scores to probabilities. We are able to make probability predictions on newly inputted data. However, recall that to make predictions on newly inputted data, first we have to train the neural network. And since we're dealing with a supervised learning algorithm, we're training the neural network based on previously labeled data. We have to make use of datasets which already have discrete labels of being a soccer ball, a basketball, or a volleyball. However, there is just one problem. Our training data, how do we actually label it? With binary classification, we simply had labels of either 0 or 1, and there were no issues of dependence among the two labels. Although, transferring from binary datasets to multi-class datasets also presents another issue. With multi-class datasets, we cannot follow the same procedure. In the case of this example, our intuition would tell us to label these classes from 0 to 2, such as labeling a soccer ball as 2, a basketball as 1, and the volleyball as 0. This seems like a concrete solution. However, the issue with this solution is that it assumes dependency between the classes. This is what's known as label encodings, which gives numerical aliases to different classes. The problem with this, label encoding assumes some kind of relation, some kind of dependence between our classes, such that our algorithm might consider these to be in some kind of order, 0 to 1 to 2, which doesn't make any sense. These classes are mutually exclusive. We don't want the algorithm to consider one class more highly ordered than the other, or process the classes with any sort of favoritism. For this reason, we cannot use label encoding. To label our training data, we use one-hot encoding. One-hot encoding allows us to classify all of our classes without assuming any dependence between the classes. One-hot encoding works by creating separate columns for each data label in the data sets and using an appropriate 1 or 0 value for each column to identify the data class. For our data, this would look like the following table. Since we're dealing with 3 classes, we create 3 columns. The presence of a class is presented in binary format. If something is a soccer ball, it will be 1 hot encoded as 100. If it's a basketball, it's 1 hot encoded as 010. If it's a volleyball, 001. As you can see, this technique allows us to create independent labels for each of our data classes and ensures that our data does not assume any relation between our classes. They're linearly independent. This can be done for any number of classes using the appropriate number of columns. Now we have gained another tool to use for classifying multi-class datasets using neural networks. Alright, so the process is similar to how we did it with binary classification. We're training a neural network based on previously labeled data which are 1 hot encoded. Using that labeled data to train our network to develop the perfect model and classifying it by updating the weights and biases of our network through some gradient descent algorithm. And then using that model, we can make predictions on newly inputted data which don't have a label and predict their probability with the softmax function of it belonging to one of the 3 classes. That is the grand scheme of things. Now that we have dealt with the logistics of data organization and data score analysis, let's begin to discuss how the process of deep learning changes when we go from a binary dataset to a multi-class dataset. We will discuss similar topics such as cross-entropy, gradient descent, and backpropagation in the context of multi-class datasets.